So we were discussing naming organic compounds the last time. You are already familiar with the stems or the prefixes or maybe the suffixes for different homologous series back from IGCSE. And the last time we were practicing some simple games. Now I was telling you some common tricks that we might have to face. Those tricks are a little bit old, but you never know when Cambridge people are going to pick up a very old question back from 2008 or 2006 or maybe 2002 and put them in their current paper. That can kind of taken as a repetition, but repetition after such a long time is really hard to predict. So moving back to what we were doing the last time. Okay, the last time I was considering these few examples and I was discussing how we commonly go with the names. So, the pretty much basic set of rules I explained back there was that you always go for the straight longest chain for carbon atoms directly connected without doubling them up in your counting. So, go with the chain. For example, this is the chain that you found out. Let's say we talk about this chain, this would be known as parent chain. And I usually use squares for parent chains and circles for branches so that it's easier for my students to pick up from whatever I'm doing or the basic sense of the whole compound. Now you can start numbering from the either side, left, right, top, bottom. It does not really matter, but the basic rule is to give either the branch or the functional group the lowest possible number. Okay, so if you really need to choose between a branch and a functional group, remember, you're always going to prefer functional group. There are very rare exceptions to this rule. Okay, so functional group should get the lowest possible number. If it is a comparison between a functional group and a branch, functional group should get the lowest possible number, and then any high number for a branch is good enough. And we were talking about a single branch that day, and I was talking about the trick. What might looks like a branch may be a parent chain like this one, because the parent chain has then 6 carbon atoms. If I went on with the straight parent chain, that would have 5 carbon atoms, and that would have been wrong. So most of you were coming up with a suggestion of a name based on a parent chain of pentane. However, I told you that the name was hexane. In the last class, we also went by a conversion of the name into structure or structure back into the name. So I told you that every part of the name serves a purpose. So you should know that purpose so that you can easily write the names. Along with that, you can also convert the names back into the structure. For example, if this is the name 3-ethylhexane, now this should tell you 3 is the position of the parent chain carbon atom to which the branch is actually located. And then we always use hyphens or dashes in order to separate the numbers and letters. Ethyl means the branch has 2 carbon atoms. Eth means the branch has 2 carbon atoms. Yl is actually the suffix for a singly bonded branch. Hex means 6 carbon atoms. Ane means singly bonded parent chain or alkane. All right. So every part of the name gives you the idea. And whenever you're supposed to draw the structure from the name, remember to start from the right hand side. The first this one is supposed to be done first in the form of simple skeletal, right? Hexane. Hex means 6 carbon atoms, ane means singly bonded. And then on 3 position, we are supposed to attach ethyl. So take it as 3 and put 2 carbon atoms to it and then fill them up with the hydrogen atoms. There you go, you're done with the structure. And that way, the rules are going to be really short. That way, you're always going to end up with the correct name or with the correct structure. Now, this doesn't just stop over here. In A levels, we sometimes, not very commonly, we sometimes have to handle with compounds that have more than one branches. And that too in a more complicated way when there are 2 branches on a single carbon atom. So we are supposed to go with both of the cases today. So let's get back to our whiteboard and let's get started. So I hope my whiteboard is now shared with you. So for an example, let's not go for this. too thick. All right. So let's consider this one. All right. Name. How would you name this? I know a new set of rule is required for something like this, but go ahead. Give it a try. You can annotate it. Let me turn on the annotations for you, or you can send me the name in chat. That's entirely up to you. If you're doing it on a piece of paper, that's fine. You can send me the picture on WhatsApp, whatever you'd like to do.
So this,
Very close, uh, a very few small mistakes, but close and almost correct. All right, let's do it the way I have been saying. Did you just erase it? Don't erase it. Let it be there. Okay, let's go with this. This is going to be a parent chain. These two are going to be the branches. If I start the numbering from right-hand side, the first methyl is going to get 3. The second methyl is going to get 5. Not correct. If I start numbering from left-hand side, 1, 2, and let me even 3, 4, 5, 6. That's how it's better. So Saad was correct initially. The only mistake Saad made was that we only separate numbers and letters with hyphens. Numbers are always separated with commas. All right, 2 comma 4, the first letter is always capital, the rest are always small. Dimethyl, remember di comes as a prefix for number of same kind of branches. So since both of them are single carbon based, both of them are singly bonded, so dimethyl means 2 methyl groups or 2 methyl branches. And yes, he was correct with the rest of the name. Okay, that's how it goes. I hope everybody understands. So a couple
yes,
of
sir.
rules. If you have uh, 2 different branches, remember you need to give 2 numbers. The number of branches and a number of numbers should remain the same. All right. So if you have 2 branches, there would be 2 numbers and 2 names, or one name must have a prefix. So since the branches are same, die, 2 numbers separated by commas, numbers and letters separated by hyphen, and so on. The rest of the name is fine. Okay, another example. What if the branches are a little bit different? My bad, this can't really be 3. That would be a huge mistake. Okay, so the point is, what if we have 2 different kinds of branches on there, on 2 different points? What then? Again, I will be telling you one more rule, because every time we change the kind of example I'm putting in front of you, I need to come up with additional rules. So for this one, the rest is same. It's just that if there are different branches, then you would be coming up with different names. Of course, that's very easily possible and understandable. So this whole is the parent chain, one branch with two carbon atoms, another branch with a single carbon atom. Numbering from left to right makes sense, right? That's how it goes. Now this time, new rule. The branches, if they're different, they're not arranged by the numbers, ascending or descending order. They're actually arranged alphabetically. So one of them is methyl, starts with M. The other one, ethyl, starts with an E. Ethyl comes first. That's going to be 4-ethyl, 2-methyl, and heptane. Now, every part of this name should make sense to you. On fourth position, we have the two carbon base, singly bonded alkyl group. On second position, we have one carbon base, again, singly bonded alkyl group. There are 7 carbon atoms total in the parent chain, and all of them are singly bonded. 4-ethyl, 2-methyl heptane. Okay. One last rule before we finish up alkanes, and that is, what if you have this kind of structure? Alkyl groups, doesn't matter if they are same or different, but they lie on the same carbon atom. A couple of rules about this one. Now, whichever way you draw the parent chain, it doesn't really matter. There are approximately 4 different ways of taking out a parent chain in this compound, and all 4 of them are correct. This one is the first one. If you take this methyl on top, second one, this methyl at bottom, third one, this methyl at bottom, fourth one. So there are 4 different ways to come up with this. Actually, more than 4. You can twist this one up every time. You will have multiple ways, much more than 4 to come up with the parent chain. But every time, if you choose the parent chain with the same set of atoms, same number of atoms, sorry, but they can be different atoms really. So you will end up with the same name. If you do, I hope you understand you're going with the correct naming. If you're not coming up with the same name, you're probably not doing the right naming. Okay. So in case of this one, one branch, two branch, 3 branches. Now, this makes sense that if we start the numbering on from this side, so 1, 2, 3, this one's 4, and this one's 5. So it becomes 2, 2, 4. And there I hit you with another rule that if there are 2 branches located on the same number of carbon atoms, the number comes twice if there are 2 branches. Okay, so it becomes 2, 2, 4 trimethyl. Again, a prefix for the number of branches, 2 di 3 tri. Of course, they're all single carbon based, so methyl and then pentane. Okay, and you are going to view this as this one. You have also seen it in the IGCSE book, though this was just written in a single line over there, but it was there. Not all of the IGCSE books, but a couple of them. Okay. So this is something that we are using currently as pattern. I hope this kind of naming also makes sense to you. If there are any questions, ask them now. Okay, not. Let's move ahead. This time, let's start with alkenes. Alkenes are pretty simple and the easiest one to follow. In case of alkenes, the rules slightly change, and so the basic rules of locating the straight chain remains the same, numbering remains the same. We actually try to prefer the branch, but that changes a little bit over here since we already have a functional group based upon a double bond. So whenever you're going to locate the straight longest carbon chain, make sure both of the doubly bonded carbon atoms are a part of it. And one of those carbon atoms gets the lowest possible number. Okay, so you would notice that this or this, you would notice that both of these are C4H8. Both of these are known as butene, but that's not the actual name. What do you name this one as? So straight longest carbon chain and 1, 2, 3, 4, right? Really, it doesn't matter if I start numbering from the right or the left. This is going to be butene. That's how we mention alkenes. So the prefix or the stem comes first, then any one of the carbon number atoms with the lowest possible number mentioned over here, and then ene. Remember, the rule for hyphen remains the same. A number and a letter are always separated by a hyphen. So of course, we're gonna do the same with this one. So this one is going to remain the same. It's just that we're gonna number this from here. So it's but 1e. I hope you understand that we will be capable of making only pent 1 and pent 2 ene. We won't be able to come up with pent 3 ene. Do you understand why we won't be able to come with pent 3 ene?
Yes.
Good. If you understand that the naming would be incorrect and we'll be coming up with the right name as pent 2 ene, I hope you get my point. More importantly, since we are going to cater double bond and branches at the same time in AS and more of that in A2, so we need to learn that too. So let's suppose if we have something like this, then how will you name it? It's actually pretty simple. This time, let's go for a little bit of a change since that's also possible. Now, you can't really start numbering from here just because the branch is going to get number 2. Remember, among branch and function group, most of the time, function group gets the preference. This becomes number 1, number 2, number 3, number 4, and number 5. So it becomes 4-methyl pent 2-ene. Remember, you don't need to put anything to separate a letter and a letter. They can either be separated with a space, or even if there is no space, it remains the same thing. Well, the more important convention is to give a space, like I've done with the L of methyl and the P of pentene. I hope this makes sense too.
Yes, sir.
If you have any questions regarding alkenes, ask them now.
No, sir.
All right, great. Let me tell you, alkynes and alkenes are named in the same way, except for the suffix change, and instead of double, there would be a triple bond. The rest of the rules for alkynes and alkenes remain almost the same, though alkynes will not be considered as much for AS or for A2. Now, there are other naming rules. For example, there are naming rules for alcohols, carboxylic acids, esters, and the nomenclature for other uh, families of homologous series as well, which are going to be new for you at AS. I specifically named aldehydes and ketones for AS. So we are going to go with that, but we'll go with that chapter by chapter wherever we require something. I'm not going to go through all the nomenclature at one point. So let's stop it right here and let's get back to the book. So I hope you understand this example. I just went for this one as 2 to, this one, by the way, is 2 to 3 trimethylpentane. I gave you an example of 2 to 4 trimethylpentane. However, if you look at this 3-ethyl 2-methylpentane, they also give you the alphabetical order uh, rule. So they go with the very basic of rules in the book, but you need to be a little bit more good at just the two basic rules. Now, take a look at this. I did go with this whole table in my last class before I started off with nomenclature, but I never explained this table. Now, if you take a look at this table, there are a couple of things that I want to explain about this table. Yeah, you are already familiar with homologous series and examples or the structural formula, but the skeletal formula is the more important thing I want to consider right now. So take a look at this skeletal formula. You understand the bends of the corners are carbon atoms, and single lines represent single bonds, and double lines like this represents the double bond. So I hope you also understand the 2-chloropropane structure and chlorine written up top. So not every bend or every corner is considered as carbon. If there are some other symbols over there, you are, instead of going to consider carbon, you're going to consider that specific symbol. I hope you understand about butane 1-ol. It's pretty easy of a symbol. And then butanol and then butanone. Aldehydes and ketones are something that are new for you. We are going to study them in detail. And that's probably the last chapter of organic. Okay, butanoic acid. Take a look at that from one corner, we have a double bond raising up for oxygen, which gives us the idea for this carboxylic acid group, and then the OH. Now you need to consider that as a whole functional group. You can't really consider this one separately and this one separately. No, that's not how it works. It works as a whole functional group, COOH, okay, or COO ester group. All right. I hope that makes sense. And about this one. Okay. This one I specifically circled. Why? Because there are 4 carbon atoms. And for the fourth one, he never gave any bends or any corners. The carbon that is directly connected to nitrogen with because of a triple bond, this specific carbon is not shown over here as a bend or as a separate corner. You are still going to consider a carbon over here. Okay, it doesn't exactly mean that this carbon is connected to this one. No, this is CH2, this one is also CH2, this one is CH3. I hope that is understandable. But if they do something like this, okay, and then this nitrogen, this also can be considered the same thing. So you can give a bend and you can write it without a bend. Both are possible. Both are taken as the same thing. Again, in IUPAC, we have a couple of rules in which 2 or 3 different cases are acceptable. Okay. So we went on with many common functional groups, their examples, or their structural or displayed formulae in the previous table. This table discussed their skeletal formulae. So I hope you understand all of those. Now, for moving on, for some functional group, no number is needed if the group can only be positioned at the end of the chain. For example, carboxylic acids, butanoic acids, aldehydes such as pentanol, Okay, I can see about that. While I'm talking to you, I can see about that. Okay, so coming back to it, I hope you understand. We never numbered carboxylic acids. We never did that back in IGCSE. We're not going to do it over here. For carboxylic acids, they are it is very much understandable. They are only always going to get the first preference. You cannot prefer any other functional group or any other type of branch over it. This would, I mean, the carbon of the carboxylic acid would always get number one. For example, if you look at this formula, let me tell you, when you're going to number the carbon atoms, this is always going to get number one, and you're not going to even mention it in the name. There is no need, because it's understandable. It would be having number one. And it's always at the corner of a chain. It is never in the center. Since esters are always supposed to be in center, so are ketones. But in this case, or in the case of aldehydes, such as this CHO, this carbon always gets the first number. They're supposed to be in at the corners. However, if these two are present at the same compound, carboxylic acid would get the preference. Okay. There are examples related to that, but remember, you will not have to name this difficult of compounds. Your naming would stick to the easiest of structures, the easiest of alcohols, the easiest of alkenes or alkanes or stuff like that. We actually explain the naming so that if that comes as a part of a question, it doesn't confuse you because of something new that you are seeing in a question. Okay. This is more of a familiarization act, not a practicing act. Okay. For difficult compounds, specifically speaking. Now, as well as alkyl groups, you will also have to recognize aryl groups. When we say the word aryl compounds actually contain at least one benzene ring. What is benzene? A benzene is a molecule which has six carbon atoms arranged in a hexagon, with each carbon atom bonded to one hydrogen atom as shown in the displayed formula. Notice this is a proper hexagon. Every corner of the hexagon represents a carbon atom, and each carbon atom is bonded to just one hydrogen atom. Now, this might not make sense to you. Let me clarify that this is a part of A2. We do not discuss it over here, but we usually draw it like this, and we draw a circle inside it. If we go to the skeletal formula, that's how it's drawn. You are going to study, or you might face this kind of shape for it. I mean, the shape is really the same. I'm just going to elaborate the bonds. An alternate of double, single, double, single, double, single for all six bonds. Three double and three single bonds all alternate one another. This is also benzene. But let me tell you, benzene's single and double alternate bonds were a part of past. Now we have proven that this exactly is not a combination of alternate single and double bonds, right? This is a combination of electrons delocalized. So in order to show the delocalization, we, instead of drawing these alternate bonds, we draw a circle like this inside. This automatically gives you the idea this is benzene. Benzene is such an important compound, or so many millions and billions of organic compounds are based on benzene, that organic chemistry, being the largest branch of chemistry, and benzene-based compounds being the largest subpart of organic chemistry. Yeah, this is a huge deal because benzene has a lot more importance than what it just seems in this simple displayed or skeletal formula. All right. So benzene-based compound, any compound having this structure as a part of it would be known as aryl compound. This itself substance is known as benzene. Now, a few of the aryl compounds have been shown over here, and also their naming. Now, if there is only one alkyl group bonded to benzene ring, like in this case, you can see methyl, so we don't have to include a number to it, and we can simply give it name, methylbenzene. Or if it's OL, benzene-based alcohol, or ketone, or aldehyde, we can keep on giving it different names. Benzene-based alcohol is again something we're going to study in A2. or benzene-based other compounds, or ketones, or aldehydes would also be discussed over there. However, if there are two alkyl groups on benzene, then we need to number it. Now, since there are two corners, or since there are 6 corners in total on a hexagon, any one of them which is more important is given number 1, and the numbering is started from a side wherever the second branch gets the lowest possible number. So number 1, if I start from this side, it gets 4. If I start from this side, this gets 4. So the numbering can go either way. Hence, 1,4 dimethyl benzene, 1,2 dimethyl benzene, or methyl benzene. This really should give you the idea that the type of benzenes that actually exist are 1,2, 1,3, and 1,4. Take a look. If we have a branch over here or here, it would be 1,2. If a branch is present over here or here, it's 1,3. And this one is already 1,4. So there are 3 possibilities. However, if there are more than 2, the possibilities increase and the numbering goes all the way to 1, 2, 3, 4, 5, 6. So there can be 3 methyl groups, there can be 4, and numbering would be done accordingly. This is how far we come for aryl group benzene or its naming. We do not explain anything on top of this. Okay. So moving on. But before I move on, any questions about this one? This naming is kept simple, right? And the book draws a boundary line here, so does Cambridge. So you don't have to go for complicated naming. Remember, you will never be asked to name complicated materials. Then those names would be a part of the question. If they're ever going to ask you name, the naming would be really simple. Okay. Some examples are given over here. Apart from what we have done, okay, the writing technique of structural formulae is something that is also important. Now, whenever you see a formula written, you can automatically understand whether the formula is correct or not. Okay, I am specifically going with question. This is question number 3, part C, to give you the idea that how do we write. Okay, now when you look at this, remember this is the parent chain that you're going with. Anything in as a part of bracket is a branch. Again, parent chain, part of bracket, branch, again parent chain. All right. The formula is for the aldehyde. It is 3,5 dimethylhexanal. Means the parent chain would have 6 carbon hex. Al means the formula would be CHO at the end. All right. And there would be 2 methyl groups, 2 CH3 groups, 1 at 3, 1 at 5. This is what the name gives us as a hint. Now, if I draw this structure, it would become CH3, CH. Now, this bracket CH3 is basically a branch present on top or bottom of it. It does not really matter whether you draw it on top or whether you draw it at bottom. Again, the second branch means the same, and that's how it goes. Now, take a look at this. This is not aldehyde. Okay, this is carboxylic acid. Definitely, that's not right. It has to be CHO, which is given over here, here, and here. Any of these 3 might be the correct option. So it's hexanal, and it has to be on 3 and 5. So this is 3, this is 5. So 3, 5, dimethyl was correct, hex was correct. It was just that it was not hexanal, it was hexanoic acid, because of which it is incorrect. So A is incorrect. Okay. Okay, let's draw another structure. I am going to draw a few to give you an idea about it. Now this is CH3, again CH, and then we have CH3 in brackets, and then it's CH2 and CH and CH3, and then it's CH, oh, my bad, it is actually CHO. Now, this obviously gets number 1, number 2, number 3, number 4, number 5. And this you can count without brackets. Remove out the brackets 1, 2, 3, 4, 5. The parent chain is not hex. You don't even need to do this further. I'm trying to explain how to read this. How you do not need to draw this entire structure. If you know the hints or the tips to solve the MCQs, you can do them quickly without even drawing them. This goes out as a wrong option because of this. It's not an aldehyde. So this was an aldehyde, but there are 5 carbon atoms. Okay, let's take a look at this. 1, 2, 3, 4, 5, 6. These are 6 carbon atoms. Now, if this is number 1, this is number 2, and this is number 3. This one is present on 3. This is number 4. This is number 5. This one is present on 5. Makes sense. This can be right. Let's check out the last one. Now, CH3 and another CH3. Now, let me show you that if I am going to draw this won't make any sense to you. How? Let me show you. CH3. Now, bracket means this should be on top of this CH3, CH3, CH2, and then this means there has to be a CH3 over here, and then CH2, and then CHO. Now, the straight chain would work like this, which means we never needed brackets with this one. The brackets are totally incorrect. Okay. Even if that's incorrect, even if I don't take it as incorrect, let me tell you, and I'm going to change the color for my own ease. This is one bond, this is second bond, this is third bond, and there are 2 more hydrogen atoms, which means this carbon is forming 5 bonds, which is not possible. Even if I don't go for the brackets, the simple rules that I told you before, 1, 2, 3, and 4, this is definitely not hex. So on multiple grounds, this is wrong. C is your correct option. Now, if you understand why wrong options are wrong, and if you know how to eradicate them as quickly and correctly as possible, this is going to become easier for you. Now, for this one single question, I gave you a certain set of tips, like 3 to 4 different tips of doing it correctly, as well as doing it in a fast way. I hope you've got them, right?
Yes.
Good, great. Moving on. Bonding in organic molecules. Now we already understand, we have done it as a part of chapter number 4, that there are sigma bonds and then there are pi bonds. Now, if we talk about sigma bonds, let's revise a little bit before we move on to the organic part of this topic. Every carbon atom has 6 electrons. We do understand, and the outermost shell has 4, and they form single covalent bonds with 4 other atoms. That's how carbon usually satisfy its combining capacity. Now, carbon atom can gain electronic configuration of nearest noble gas by doing so. So these single covalent bonds are also known as sigma bonds. Now, the pair of electrons in a sigma bond is found in a region of space described as a lobe between the nuclei of 2 atoms sharing the electrons, which usually, since it was p orbital, we described it as, my bad, as a head-on-head overlap back there in chapter 4. Now, the electrostatic attractions between negatively charged electrons and the two positively charged nuclei, this one in this case or this one in this case, actually bonds the atom to each other. So they try to attract the electrons. In many organic compounds, each carbon atom forms 4 sigma bonds. The 4 bonding pair of electrons, which are all areas of negative charge around each carbon atom, repel each other. Now, this repulsion is very important to understand the arrangements that we're going to give them, as well as the angles. We have discussed the same point back in Whisper or Saper theory, valence shell electron pair repulsion theory, and we're talking about the same thing over here. All right. So these electron pairs, for example, in this diagram, we have this pair, we have this pair, we have this pair, we have this pair. These pairs are all going to repel one another on the same nuclei of this carbon. So they are supposed to be as far apart from each other as possible. And in doing so, they will actually keep the repulsion at minimum and hence become a stable molecule. Now, that is supposed to happen with a tetrahedral bond angle, which is 109.5, and which gives us the idea for this. Now, whenever we go down from 120, okay, and we go with 109.5 or 107.5 or 104.5, anything like this, we do understand that we're talking about a 3D bond. And when we're talking about a third dimension, that automatically implies that there would be something that would be a part of plane. And remember, in any molecule, the part of planes are shown like this, usually the simple bonds, okay? And something that I keep saying towards you, and the book says uh, sticking out of the plane. These are the words that book is going to use. We show it with a wedge, okay? And the wedges are usually filled up with colors so as to not create any confusion. Now, the one for which I say away from you, and I have given an example of 3D cinema. If you have seen a movie in a 3D cinema or on a 3D basis, you would understand what coming towards you or going away from you or sticking out of the plane or sticking into the plane means. Now, these are the two parts of the third dimension that we keep talking about. So that is usually shown with a dotted line. You can also show it as a dashed line. The dashes are supposed to go like a wedge, a little bit smaller at the start and bigger at the end. Okay, so the dash, the dotted line means away from you. So that's how the entire three dimension is shown. So this gives you the idea what's happening over here. Now, I hope you understand that we understood the part of chapter 4 where we discussed the hybridization. And this angle automatically gives you the idea that it's sp3 hybridized, something which is really isn't mentioned over here, but is mentioned as a part of caption over here. Okay. So I hope you understand that these are not simple atomic orbitals, these are actually hybrid orbitals, for which the result is this ethane molecule. Now moving on, pi bonds, carbon can form double bonds or triple bonds. I hope you remember that for a double bond, there was one sigma and one pi bond in total. That's why we called it a double bond. And for a triple bond, there was one sigma and there were two pi bonds for a triple bond to happen. Now, double bonds, carbon-carbon double bonds, alkenes such as ethene, and they explain the sigmas and pi's. For a triple bond, of course, this is going to be different. Now, I hope you understand this is sp2 hybridization and this is sp hybridization. Now, sp2 clearly means that there was one orbital that never took participation in hybridization. And that one atomic orbital, which never got hybridized, was the sole reason of this pi bond. Why? Because that was the one that went with sideways overlap. I hope you understand that sideways overlap was something like this, which had this kind of probability of electron. And this lies the line. Definitely, the electrons are not lying on the central line of joining the two nuclei, but on top and bottom of it. That's why we were actually trying to show them with something like this. And I used to call it a lip-based structure. There is an upper lip and there is a lower lip to give you an idea about it. So I hope you do understand the complete explanation for a double bond. There is a triple bond a part of Cambridge, but Cambridge usually sticks to asking more detailed question about double bonds as compared to triple bonds. Okay, if you're going to look up past papers, you'll see the same thing. So now p orbitals and pi bond has been explained in the same way. Now your book in chapter number 4 initiates with almost 120-degree angle. But then in the example of 15, they tell you that it's approximately closer to 117 degrees. So wherever the question is about 120 degree and an option is given closer to 120, choose that option, that's fine. But if they are asking you to be more specific and the options lead to somewhat closer to 117, you can always be more specific. Remember, you need to work at it vigilantly as the examiner is asking you to. Don't come up or make a hard and fast rule of going with one single answer as your only possibility. That is the biggest mistake student make. मैं बहुत क्लियरली बताना चाहता हूँ स्टूडेंट्स बहुत हार्ड एंड फास्ट रूल बना लेते हैं कि मैं तो 120 लिखूंगा दूसरा एंगल याद ही नहीं रखते and when he tries to change the question with a clever kind of wordplay they stick to their hard and fast rules and those rules actually get their marks cut and then by the end of the day they say मैं तो ठीक लिख रहा था उसने पता नहीं क्यों काट दिया नहीं you can't be stubborn about a fact. It works in the same way. If the examiner is talking about 120, write 120 as an answer. If he wants to take the 117 degree or closer to that accuracy of an answer out of you, go with that one. Don't be stubborn about 120. All right. I hope that clears it up. Now, again, the two lobes up and below the pi bond is something that I've already explained. The 120 case I've already explained. If I talk about a triple bond, I hope you understand that the structures usually are linear and the angle is usually around 180 degree. And an example of a sine, or if we go back to chapter 4, instead of a sine, they took the example of HCN in that chapter. So whether you talk about HCN or whether you talk about the example of a sine, it actually is almost the same thing because the structure, the linearity, or 180-degree angles, or how a triple bond is supposed to be a combination of actually one sigma and two pi bonds, and how two different p orbitals do not participate in bonding and they end up with an sp hybridization only, is also all are part of these. Now, uh, a couple of things that I mentioned here in the book, and I'd like to go with. The two lobes of one pi bond lie above and below the plane in the atoms of ethine molecule. So one of them is above and one of them is below. Again, one of them is above, one of them is below. The two lobes of other pi bond lie in the front and behind of the plane. That is another way of telling it. If you're talking about as a whole in three-dimension pattern, telling one of them above, one of them below, one of them in front, and one of them in behind gives you a very good idea how that works. Means it is surrounded from four sides and not just top bottom. Means it does not work as a reinforcement. They all have their own separate places. Why are we trying to talk about this point in such a emphasized way in order to give you again the same point? Whisper theory, the pairs or the electrons are going to arrange them in a way that they are farthest from one another and keeping the repulsion at a minimum and keeping their stability maximum. Remember, the lesser the repulsion, the maximum the stability. So this maximizes the overlap of p orbitals, which in effect form a cylinder of electron density around the two carbon atoms. Ethine molecule is linear in shape and it is actually arranged in a straight line. Linear and straight line means the same thing. I hope this explains this completely. Next up is structural isomerism.